Hey guys, today we're going to take a look at the dot product of two geometric vectors. Okay. So your first question, of course, is what is a dot product? I'm glad you asked. The dot product, okay, of two geometric vectors A and B with an angle of theta between them. And that's when they're positioned tail to tail. You have to put them tail to tail to find the angle between them. Is a scalar. Okay, is a scalar defined by. So this is the important part. So the formula for dot product is A dot, which you'll notice sometimes, in math we use, like the X style product or a dot style product, and we use them interchangeably. In this case, it's called the dot product because you have to use that dot notation, because the cross product, we call the other one, is something else that we'll learn later. So you're going to take the magnitude of A, and you're going to multiply by the magnitude of B, and then you're going to multiply that by cosine of the angle between them. And that's it. It is sometimes known, as the scalar product. And if I'm being honest with you, I've never heard it called that in my life, but it said it in your textbook, so I thought I should include it. I don't know anybody that calls it that. But anyway, that's the gist of it. That's the most important part of the lesson today. If you can remember that, you'll do just fine. So we're going to do a little example here. If we've got a magnitude of 4 for u, a magnitude of v for 6, and an angle of 120 degrees between them, what is the dot product? So first of all, it will be, so we go u dot v is equal to, and we've got 4 times 6 times cos 120. Okie doke. And that's just going to give us, you can just plug that all into your calculator and you'll just get that it is negative 12. And that's it. Okay? So not super difficult. Okay. Although we will use questions that make it more difficult, such as what is the angle between two vectors so they're unit vectors. That's important, of course, because that means that their magnitude is 1. Okay. And we know their dot product is 1 over root 2. So in other words, so we will write this out the whole way. I'll stop being lazy for a bit and I'll actually write this out properly. So we've got u v cos theta. Okay, so we'll write down what we know. So the dot product itself is 1 over root 2, which is equal to 1 times 1 times cos theta. And we're looking for theta, of course. So these, obviously, we can just ignore those. Okay, and we want, whoops, nope, that's not what I want at all. What I want is theta. So theta is going to be the inverse cos of 1 over root 2, which hopefully you remember your special triangles well enough to remember that that is just 45 degrees. Okay? And you can give me that in radians too if you prefer, but at the moment I don't really care. This mostly is going to write stuff out in degrees. Okay? But you should know both, I guess. Anyway, so there are some properties. So property number 1. There's actually, I have a whole bunch. I've got 12 properties for you. Okay, so number 1 is that the dot product is a scalar. Okay, and I had already mentioned that, but it is worth saying. Property number 2. If A is parallel to B, perpendicular, then A dot B, okay, the dot product will equal 0. And this makes sense because, of course, cosine of 90 equals 0. Okay. Number 3, if the dot product equals 0, if A dot B equals 0, then Well, then we got three possibilities. either the magnitude of A is 0 or the magnitude of B equals 0 or the angle is 90 degrees. Okay, or they're perpendicular rather. So I'll say A is perpendicular to B. Okay. One of those three things must be true. Although, theoretically, I suppose they could all be true. Well, no, they can't all be true because you can't be perpendicular if you get a zero vector. But anyway, 4. Okay. If theta is between 0 and 90 degrees, then the dot product is going to be greater than 0. Okay? So that's, yeah. And number 5. And that makes sense because magnitudes are always going to be positive, and if the angle is between 0 and 90 degrees, then cosine of theta will be greater than 90, or will be greater than 0. So similarly, this one probably doesn't need to be said then, but I'm going to say it anyway because I'll do whatever I want. So there we go. If the angle is between 90 and 180 degrees, then you'll notice I'm spelling then with an E. That's because I understand the difference. Anyway, you're going to get a negative number for a dot product. A negative number for a dot product. And again, that makes sense because cosine of angles between 90 and 100 or 180 will be negative. And since both magnitudes will always be positive, that's all that matters in that case. Okay. So number 6. If I'm going to use a symbol that I think is self-explanatory, but I'm going to explain it anyway. Okay, that means parallel, right? But I'm going to put arrows on the end. So they're collinear, but they're also going in the same direction. Okay. Then theta equals 0 degrees. And thus, because cosine theta would then equal 1, then the dot product, oops, oh, did not mean to put those. So the dot product is equal to just the magnitude of A times the magnitude of B. Okay. Because cosine equals 1. Okay. Number 7. If, again, we get two collinear, but this time they're going opposite directions. Okay. Then we would describe theta as being 180 degrees. And thus, when we take cosine of 180 degrees, it would be negative 1. So the dot product would be equal to negative of the product of the magnitudes. Okay. There we go. Whew. Almost there. Number 8. If I have a vector and I take the dot product of it with itself, then that is just going to equal the magnitude squared. And that makes sense because if we use rule number 6, of course, that would apply, because they're obviously going in the same direction because it's the exact same vector. So that follows from number 6. Number 9. The dot product of A times B. And this might seem obvious, but it shouldn't seem obvious because it's often not true in this kind of stuff. But the order for this doesn't actually matter. And we have a name for that one. We call that one, I'll write it in blue so it stands out. This is called commutative property. Commutative property. There we go. So, what else we got? We're almost done. We're 3/4 of the way down these. There's only 3 more. So number 10, we've got what we call the distributive property, which is the same as all the distributive properties you've learned up to this point. And if you do that, the dot product of that times b plus c, that would be the same thing as taking the dot product of a and b and adding it to the dot product of a and c. Again, that might seem obvious, but it shouldn't seem obvious because this is a rule that is often not true. So that is the distributive property. Distributive property. All right. Number 11. We got this guy. So we got a k, which is a constant. Okay, and we multiply by a, and then we take the dot product of that vector times b. That would be the same as k. Whoops. K is a constant or a scalar times a b. Okay, so I can take the dot product first and then multiply by that scalar, and it will give me the same answer. It will, of course, also be true that a dot k times b. So you can multiply that scalar in whenever you want, and it won't make a difference. Okay, and the last one, the best one, if I have a vector and I take the dot product of that and the 0 vector, it will equal 0 always. Okay? Notice this one is the 0 vector, and this one is just the number 0. Okay? Those are different things. Do not forget that. All right. So, all those properties, what I want you to do is I want you to attempt to prove these 4 identities here. Okay? There's also a challenge question at the bottom. I'd like you to give those all a whirl, and we will take them up in class. So until next time, go Sabres.